So I'm really excited to be here, and thank you all for filling out the room. As Garrett just said, I am Kushal Pisavadia, and I'm here to give you an introduction to schedulers. Before I do that, I'm going to briefly talk about what I do day to day. So I work for the Government Digital Service, which is an organisation within the Cabinet Office. The Cabinet Office is a central department within the UK's civil service. And the civil service has been granted executive powers by the Queen, and that means I work for the Queen. So GDS started by building gov.uk. If you go to gov.uk at the moment, it looks a bit like this. It replaced older sites like DirectGov, BusinessLink, and many others with a simple single site for the public to use. It's the best place to find government services and information online, but we're not just fixing websites. We also build and run digital services, which means building them from the ground up, or working with departments across the country to improve their current offerings. So things like the register to vote service, where you can register to vote for an election within 5 minutes on your smartphone while you're hanging around with some friends in the park. It was used by lots of people early this year, but we had the general election, in the lead up to the general election, that is, and it saw a peak during the pre-election period when Question Time announced it, and it saw about 200,000 people all try to register at the same second, I think we had live at any given second, from about 11 o'clock till midnight, which is really impressive. The other thing that we do is provide visibility to a lot of the government services that we offer. So here you can see vehicle car tax renewals. We've got information here on the transactions per year, the total cost, and the cost per transaction. We also show the live service usage, so you can see how many users on right now. I really like this screenshot because it shows 39 users online, but the date underneath says 8 a.m. on 25th of December. Some people on Christmas morning prefer to do their car tax. But I'm not going to talk about any of this. If you're interested, you can hear more about what GDS is doing from my colleague. He's called Phil Potter, and he's sitting right there in a blue shirt, and he's speaking tomorrow on registers in this room at 3:30. It's really interesting as a project because it's the core building blocks of data that government may begin to use and should start to use to open out the information that we hold right now. But like I said, I'm not going to talk about GDS. I'm here to give you an introduction to schedulers. And one of the motivations for this particular talk is because it's been hard to go to a conference for the last 2 years without hearing about this thing. It's everywhere. And it's, from my point of view, it's starting to get a bit annoying. But there was a discussion that I was part of not long ago where someone said the pace of change in this space is too much, and schedulers feels like it's too daunting a topic to even begin to understand. So I want to do this talk to demystify a lot of this kind of area of schedulers. So things like Mesos, Marathon, Kubernetes, and Swarm. I want to help you understand when you should use schedulers and when you shouldn't. But more importantly, I want to show you how they work. The other personal reason I'm giving this talk is because, much like the young boy in The Sixth Sense who sees dead people wherever he looks, I see schedulers. Now, I'll explain this later in the talk, but that's one of the biggest personal reasons for giving this talk. The talk is structured in 3 parts. I'm going to introduce schedulers, I'm going to talk about the Kernel CPU scheduler, and then I'm going to talk about some other schedulers building on that information that you already then know. The other way to look at the structure of this talk is there's 3 questions. What are schedulers? How do I use them? And how do I spot them? The third one is really important because, as Garrett suggested at the start, many of you use schedulers day in and day out. You just don't know them and you don't know how to spot them. And I hope to help you figure that one out. So let's start from the ground up. The job of a scheduler is to fairly allocate work. And I want to emphasize that word, fair. Fairness here is an artistic term. It's used in a lot of academic literature around schedulers, but it's an important word here. It's not about statistical fairness. It's not about probability or any other kind of game theory terms that you might be familiar with. But it's a way of saying that schedulers are dumb. They optimize whatever you tell them to observe or act upon. That's it. So don't judge them beyond that. There are 3 stages for a scheduler. There's a scheduling step, an allocation step, and then a binding step. Scheduling determines the sequence in which operations are executed. What is the order? Then there's an allocation step where you set aside the appropriate number of functional units. What do you need to complete the work? And then the third step is the binding step, where you assign those operations to the functional units, where you do the work. 3 stages: scheduling, allocation, binding. So let's schedule with a simple example. Let's schedule an equation. So E equals AB plus CD. So if we were to replace the letters here, A, B, C, and D, with numbers, 1, 2, 3, and 4, from your school education, you might do something that looks a bit like this. I've put brackets in to emphasize the ordering here. In the UK education system, this is referred to as BODMAS. Brackets orders division, multiplication, addition, and subtraction. But it's just a way of saying that you have to complete the multiplication here before you complete the addition. But the other way to describe this equation is as a tree. So you know that to get to E, you have to do some addition operation, and then before you can do the addition operation, you have to complete either A times B or C times D for those operations to be completed. And addition here is commutative, so the ordering here doesn't really matter, and I'm going to come back to this diagram a few times over as I describe some common scheduling problems. So I've picked 4 to talk to you about today. There are many. There are books and books and books. I've bought a lot of them in my preparation for this talk, but I wanted to pick on 4 because they're the easiest ones to explain what you need to know. There's the unconstrained scheduling problem, where essentially you don't really have any care about the work. You want it done eventually at some point in time. You don't mind how a schedule decides what to do. So whether it has 2 multiplication units or 1, it would have to do either one of these operations, then the addition unit, and then the work will be completed. Now, there's a time-constrained scheduling, where you might want all operations completed within a finite number of steps. So I've picked 2 here. So if we take, again, the same diagram, and we chunk it up into 2 steps, we know that to complete everything in 2 steps, we'll need at least 2 multiplication units, so we can parallelize those operations, and then at least 1 addition step. Everyone with me so far? Cool. And then there's the resource-constrained scheduling step. So let's say we only had 1 multiplication unit and 1 addition unit. We know that we can only do so many things at a time. So in our example here, we would have to do a given multiplication, then another, and then finally complete the addition step. So we've seen some common scheduling problems already. So let's look at some common scheduling algorithms. You've got things like the as soon as possible, or ASAP scheduling, where you do each operation one at a time into the earliest possible control step. The as late as possible scheduling algorithm, where you do each operation one at a time into the latest possible control step. List scheduling, which is a really common choice for solving the resource constraint problem that we just saw. So where you'd schedule each step sequentially, choosing each operation based on your constraints, whatever they were. And then force directed scheduling, where you would distribute operations according to a weighting. Most commonly this is time, and that's how most people tend to realize it. So things like choosing a weight for each operation in the case of your various MapReduce jobs. So you might want one word count to be completed faster than another in Hadoop land. There's also bin packing, where you want to either minimize the number of units used or minimize the number of units left idle. This is really important with regards to container schedulers. And I was trying to find a good example of how to visualize this, and the best one I found was Tetris, because it's kind of perfect for this. So as you can see the blocks are filling out, we're trying to complete each row and fill up each row as we play the game of Tetris, and that's kind of the idea, the very, very simple idea of bin packing. Bin packing is really important because we don't effectively use our infrastructure. If we could, well, if Amazon could do that for AWS, they might stop selling books, for example. But they could concentrate on one of the bigger cost points for them instead, which is electricity usage. So now we know the basics. let's apply it to something a bit more concrete. Let's look at the kernel CPU scheduler. So, like I said before, the job of a scheduler is to fairly allocate work. In the case of a CPU scheduler, it manages multiple operations and decides which operations get the CPU utilization right now. The real challenge of this, of course, is to make sure applications get a fair share of CPU time. For some CPU schedulers, not all, they refer to this as a time slice. There are many implementations which use different terms. I'm using this one for now, and I'll use a different example later on. So there's that word fair again. So the kernel needs to share the physical CPU or CPUs among many applications running as far as the user is concerned at the same time. Now, the way that the kernel does this is it virtualizes CPU for you, because you, as the user, can't really be trusted. The basic idea is to run one process for a little while, then run another one, and then another one, and so forth. And by time sharing the CPU in this way, virtualization is achieved. If you wanted to, if your interest is writing C in kernel code, you could write one of these in a few hundred lines of code in a very, very naive way. You'd essentially take syscalls that you'd provide using libc, and in a round-robin format, just flip through each process based on the syscalls that it's asking you to complete. And as a result, a CPU can then be really happy doing what it's designed to do well, which is run one or many threads of operation, and it can keep on ticking along just fine. So let's look at a slightly more concrete example of a CPU scheduler now. Let's look at the Linux 2.4 CPU scheduler. There are other good operating systems that are available. I just picked Linux because I like it and know it. Now, if you look at the 2.4 CPU scheduler, the kind of structure that it used underneath was a task list containing all of the processes and all of their work that needed to be completed. And there'd be a single read-write lock over the whole thing. So what the scheduler would do, it would look over this task list, it would select a task to execute based on some criteria, some algorithm, some of those that we've seen already, and then it would pick one to run. Now, the criteria commonly that you might know and be familiar with is the priority of the task. So the priority tells the scheduler how to organize the processes in this queue, and using this lock, it would unlock the queue to read through or to write into it, and sort the process list based on that priority and pick the operations to run based on the priorities. So the priority tells the scheduler how to organize the processes, the process operations. But the 2.4 CPU scheduler had a number of shortcomings. The biggest one is it wasn't efficient. It had to iterate over all tasks in the task list every single time. If our task list was huge, it would use up a lot of time just trying to read through each time and seek through that entire list. It's also really bad in multi-process environments. So a lot of time was spent swapping in and out of the task, where you'd probably pin a single CPU and leave, let's say, the other 7 CPUs, if you had 8 CPUs running, unused, whilst this single queue is being inspected. So it was rewritten in 2.6 by an individual called Ingo Molnar with a lot of help from the wider Linux community. The goal was to easily handle multiple CPUs and to perform independently of load. So instead of this structure of a single lock and a big list, it did something that looks like this. It took the priorities that you have for various different processes, which are 1 through 140, and it gave each one its own queue and each one its own lock. This was a significant improvement, but it wasn't great. It still wasn't perfect, so it was rewritten again in 2.6 and later version of 2.6, and it's called the completely fair scheduler. There's that word fair again, by the way. In this particular case, it uses a red-black tree instead of a bunch of queues, and it's really interesting if you want to see all of the main list discussions from 2.4 to the various 2 implementations of 2.6 to today, because they're still all available on Gmail, and you can read all about them. And the back and forth between both the Linux community and the BSD community around the schedulers is also really, really interesting. But I'll leave that as an exercise for you to investigate. And I definitely if you're interested in this kind of stuff, I'd highly recommend you look at the FreeBSD scheduler as well. But before we saw some common scheduling algorithms, ASAP, list, and force directed. Well, these are the terms that are used in academic literature in the scheduling world, but they have counterparts in the kernel CPU scheduler. They have these names. Sched _ is the prefix for things like FIFO, RR, and other. FIFO being first in, first out, RR being round robin, and other is userland. It's what many of you tend to exist in with your day-to-day applications. They also have shorthands that you might have come across already. So things like TS, FF, RR, and question mark. Now, if you ever see question mark as the scheduling policy, be slightly worried, because it usually means there's a bug in your scheduler. So you maybe look at your documentation or rebuild your respective OSs. But if you wanted to understand what scheduling policy is used for your various different processes, you can use a whole host of simple tools to do that. So with PS, you can look at the class for the given command. Here you can see just a very short list that I've generated, looking at a few of those right now. You can also control how the kernel schedules your processes. Some of you might already be familiar with NICE, where you run a program with modified scheduling priority. And here's an example where I run echo hello with a different scheduling priority than the default. NICE is a historic utility, really. It was used in the early days of mainframes, and it's a way of being nice to your counterpart and to reduce your CPU consumption. But that's really about batch computing, and those days might not necessarily apply to us today. It's still in use, however, and it's still useful, but it only applies to the processes that run in that other scheduling policy that we saw before. There's another tool that is a superset of NICE, and that's called CHRT, or change real time. And with that, you can manipulate the real-time attributes of a given process. So in this small example, I've just printed out the scheduling policy for the process at PID 16. So it's got, the policy is first in, first out. The priority here is 99. But using CHRT, you can essentially define these things together. And I've got a small comparison here of NICE and CHRT. So if you've ever used NICE to deprioritize a process or increase the priority of a process, you can do the same thing with change real time, and you can change the actual respective scheduling policies as well in that process. The other NICE utility that you can use is IO_NICE. So if you're ever doing any backups that you find cause you some issues at 3 in the morning, cause you to get woken up, you might have used this application, this tool to either idle a given I/O for the disk I/O, for example, for a given PID, or to minimize the priority for a given process as well. But like I said earlier on, I see schedulers wherever I look. And it's this thing, it's this structure again and again and again. A queue or many queues, a lock, and then some kind of selection algorithm over the top. So we've seen very briefly with the kernel CPU scheduler, and it exists in networking land as well. So if you've not come across this, it's somewhat out of date in certain areas, but the Linux Advanced Routing and Traffic Control how-to exists at lartc.org, and it's just an excellent online manual. And if you want to know more about how Linux networking works, it's probably a really accessible read to go through as a website. And in there, I want to pick up on a particular chapter, and that's chapter 9, where it goes into queuing disciplines for bandwidth management. So it's that same structure again. So things like IP route 2, IPsec, multicast routing, all of these are backed by a scheduler which have queues and a selection algorithm. So let's look at an example that you might want to do yourselves. You might want to make the network scheduler imitate a higher latency network. Let's say a mobile phone, because you're an Android or iPhone developer, or you're doing something using mobile websites, and you want to test how your respective services respond. So there's a tool that you can use to do this. So this is the command. Everyone understands what that does? Yeah? So this is a tool called traffic control. The shorthand is TC, and I'm now just going to describe what that command does. So you invoke it using TC. The next keyword along is queueDisc, which is short for queuing discipline. So whenever the kernel sends a packet to an interface, it's queued against a queuing discipline, and everything commonly starts at the root node, and then there are various different classes that back off depending on what you're doing. So if you've ever done any packet filtering, you tend to add a queuing discipline onto whatever your network device is in that particular case. Then what you're doing here is you're adding against the local device on the root node here, a new rule to the local device here is what we're adding, and then we're setting a network delay of 500 milliseconds. NetM here stands for network emulation. So if you wanted to, you can set this to whatever delay you wanted to do, but then you can then delay all of your traffic if you wanted to. So we know a bit now about CPU and network schedulers, but there are schedulers beyond CPUs and networking. Some of you might use a database. One example is Postgres, I'm going to look at. So Postgres has something called auto vacuum, and you might come across it before. It automates the execution of vacuum and analyze commands. The commands on your tables, that is. The actual auto vacuum process can be tuned and it can be configured depending on whatever your needs are, but by default, it just runs according to the default scheduler. And if we look at the docs for Postgres, which if you haven't, are incredible, and as documentation for any database goes, it's like miles ahead of anything else. The documentation, I'm just quoting directly from it. There is a persistent daemon process in charge of starting auto-vacuum worker processes for all databases. It will distribute the work across time, attempting to start one worker within each database every defined seconds. And that sounds a lot like a scheduler to me. And if you look at the code for Postgres, that's exactly what it's doing underneath. But at the start of this presentation, I said one of my motivations for this talk was containers and some of the container schedulers. So let's look at two of them. Let's look at Kubernetes and Docker's Swarm. And let's try and look at the actual code here. So here's some Go code. If none of you have seen Go before, I'll try and describe what this is. So it's creating an interface here called scheduler. And the interface scheduler expects a single function to exist called schedule. And in this case, it takes a pod, which is some configuration for a node, and then some way of listing out all the minions or all of your respective nodes that you want to deploy onto. Docker's Swarm does something very, very similar. They just happen to use different words, and in my opinion, they're identical. So again, it's written in Go. We've essentially just changed scheduler for placement strategy, schedule for place container, pod for container config, and then an array of nodes to apply onto. In the case of container schedulers, they optimize for the bin packing problem. It's this thing that we saw before. So this idea of placing a thing based on some requirement in a very, very simple way. Now, with many schedulers, they optimize in a very, very simplistic manner based on whatever you tell them to observe, some kind of primitive. So in the world of container schedulers, they might have primitives like CPU or number of instances, and then you can choose to add your own, like response time. And all of these things are tunable because schedulers are very, very simplistic things. So it's up to you to define what good looks like. So in the world where you define what good looks like, you might have some kind of ephemeral node with some kind of service running on it, maybe some other kind of service running on it, and then all of a sudden you want to run many ephemeral nodes with many services, but because it's the cloud, these ephemeral nodes aren't ephemeral because we've chosen them to be. They're ephemeral because it has bad I/O, or you've got a noisy neighbor on there, is the reality, and we can't trust any of this stuff, and that's maybe why we hand or choose to hand a lot of this power of control down to a scheduler. And in the case of the scheduler, what it would do is understand whatever your primitives are that you've defined of what good looks like, and then move things around depending on what your requirements are. So it would move your services across depending on what you need. But I'm not going to talk in great deal about what Kubernetes or things like that actually do. If you are interested in, there is this individual called Kelsey Hightower, and he's been probably spending like the last year now just helping people learn how these things work, and most of his talks are about demos. And if you're interested in like understanding how a lot of these container schedulers work, he's got loads of really interesting talks that show you how they work and try to introduce sample applications. So things like a given Java app running Postgres, how to do the kind of cloud-friendly, cloud-native databases that might attempt to do some kind of eventual consistency systems. But yeah, his videos are excellent and always entertaining. So if you're interested in that sort of stuff, you can definitely check out Kelsey's talks. But we've covered the CPU, we've covered networking, we've covered databases, we've covered containers where you might run some of these things within, and we can keep on going up the stack. So this is a photo of baggage claim at an airport. And I don't know about you, but every time I look at baggage claim, I think it's just a load of queues with a lock. And in my case, I am the selection algorithm because I know what I care about, which is my bag. But many baggage claim systems at airports are run by pieces of software. So if you came in from abroad and you flew into Terminal 5 today or yesterday, the entire baggage claim system for Terminal 5 is a scheduler. It's a bunch of queues with a lock on them, and it's an application that uses the CPU, a scheduler. It speaks over a network, a scheduler, to a database, a scheduler. There are other examples as well in the real world. Premier League football games are set by a scheduler. So before the start of the season, a computer decides which games get set. It decides based on the competitions that various teams are in, so things like the Champions League, Europa League, or the Premier League, and also on a few special circumstances. Things like you can't have both of the big Manchester teams playing at home on the same day, because that is Manchester United and Manchester City, because you can't have, there just aren't enough police in Manchester to deal with that kind of influx of traffic. The train stations can't handle that kind of load, and it goes beyond just football. And there are a lot of interesting problems in this space. So this is an aerial view of Trent Bridge in Nottingham. And in this photo, you can see Nottingham Forest with their ground, and also Trent Bridge cricket ground. And it turns out you can't have both of these events playing at the same day as well, because there's a very, very narrow bridge that you have to cross from the train station or by car to get there in a lot of cases. But just out of shot is also Notts County, who also have a fairly large football ground. So you can't have all three of these teams playing at the same time. And it's a really, really interesting scheduling problem. How do you deal with that kind of movement of people across trains, cars, space, whatever it is? It's a lot slower, but it's an infinitely complex problem where it's probably a good decision to offload that to a computer. And like I said, I see schedulers wherever I look. And maybe you start to agree with me, and maybe you don't, that's okay. But the job of a scheduler is to fairly allocate work. There's that word fair. But there's a schedule that I've missed. There's an entire family of schedulers I haven't talked about. There's the person that wrote the code, and they schedule their own time. They probably have their own algorithm, Pomodoro, brute force, time constraint, whatever it might be. There's the person that planned the work, and they would have their own fair approach based on their own objectives. And then there's the person that asks for work. So why are we so willing to trust the software but find it harder to trust the people around us, even if they wrote the schedulers in the first place? It feels like we should be able to do better here. You can choose to hand over knowledge work to schedulers, but they're not a silver bullet. They don't solve all of your problems magically. They work to whatever objective that you set, and they optimize decisions based fairly according to your own rules that you set. So you can probably do a better job of handling certain things over a scheduler. They're not perfect. You can probably do a better job of capacity planning, because you can choose which of the primitives and trade-offs matter to your organization, whether that be money, time, resource usage, uptime, CO2 usage. Are we friendly to our environment? And based on the context of your business or your organization, you probably want to control that instead of handing it off blindly to a random computer and giving it access to your AWS tokens. So don't blindly give all control to a scheduler. Think about what they're good for and where they can help you. They're great where decisions would be too slow to give to a human. You don't want to hand that to you don't want to hand the person scheduling. Well, you don't want to hand over scheduling CPU operations to a person. So don't blindly give up all control. And even worse, don't blindly believe a vendor pitch about schedulers. For the last 2 years, we've heard a lot about containers, and we're only going to hear more and more. Big organizations have seen that there's money in this space. Just be wary. Don't trust everything. Before I finish, I just want to end on this brilliant quote from Eileen Webb. How much of the work that we do is actually a device to help us focus on what's really important, to help us fairly pick on what to work on, for us as individuals, based on our own objectives and our aims. So thank you for scheduling your time with me, and it's been great to be here.
So it's time for questions. I see we're recording this. Yeah. Great. Who's got a question? Question. Here we go.
Hello. So this is working? Okay. So you talked initially about the 3 stages of scheduling algorithm: schedule, allocate, and bind. Which one is the most complicated in your opinion?
In my opinion, I'd probably defer to all the things that I've read, and all of the things that I've read tend to disagree, which is really interesting, because, and all of them believe they're right, which is the other weird thing about a lot of the literature. And there are loads of just books that try to describe the problem in different ways, and it's kind of context specific on whatever the problem is that you're approaching, is where a lot of them tend to agree on. So in the case of CPU scheduling, you tend not to worry about the kind of initial scheduling step because other processors are giving you that information all the time and saying, go do this work for me. So it's kind of the allocation level there, that's the biggest burden. But things like the kind of football sports schedulers, for example, that I showed before, the problem there is more around understanding the entire complexities of what there is and potentially missing things out. So I guess, sorry, I know it's a really bad answer, but it just depends on your problem.
So you mentioned in your talk that there's an interesting discussion about the Linux 2.6 scheduler. Well, I find that simply by typing those words into Google.
Yeah, so that's one of the things. So I thought about linking to it, but there's a lot of interesting places that you can look at, and other people have written blog posts describing the history of these things and tried to link and reference them that you'll be able to find.
All right, cool, thank you.
Otherwise, just look for Ingo Molnar, because he tends to be the person that merged most of the top level limits of that work. Ingo Molnar, I-N-G-O is the first name, and Molnar is M-O-L-N-A-R. Cool. Any other questions?
Yeah, I have a question. So I had a problem of organizing conference talks so the tracks and the order. So that sounds like a scheduling problem, classic. And I tried to just naively do some sort of solver, like I give weight to different things, and then and I gave up after maybe a couple hours. And so I think I should probably be leveraging something there because I didn't. This is probably a lot of research in this area that I didn't. So
yeah.
And it's something like that where you have maybe a scheduling processes would seem on its face relatively simple. You could do like round robin or whatever. But a case where you have a lot of different weights, the case of the football, the matches, and all the different variables and weighting, how would you, what are some of the like fields that you would approach there? What, like if you go research and learn more about actually doing that?
I don't know. In the case of that, I wouldn't necessarily go to academic literature. Where I'd go is I'd probably, I mean, we have a number of people here who've come to the conference who would have paid to attend, and they were interested in certain topics. So in that particular case, you probably want to ask your attendees. You already know ahead of time that they're attending because they've paid. So you can just get them to vote based on what they are most interested in, and just kind of map that out accordingly. Because it's a bin packing problem then in that case. It's here are the interests, are they aligned? You can't meet everyone's needs, but you can do the majority at least.
Well, so in this case, it was like length of time, and there was a bunch of other ways, like more kind of logistical issues as well. And it wasn't like a simple voting. It was a solver that was like I looked into the solver space. Does that apply here? Is that like your Tetris, for example, the Tetris model which you use, which has to do some sort of analysis and perhaps weighting of best fit? Is there like what's the Tetris algorithm?
Well, there's loads. I don't know. If I'm honest, right now, what I'm thinking about is what are people interested in, because that's the biggest thing. Like as much as having the perfect schedule, like and fitting everything in based on time matters. The reason the conference exists in the first place is because people want to attend it, and it feels like that's the core thing to push towards first and have an understanding of. Yeah, and then using that information gives you the kind of core primitives to weight things on. So then, based on interest, then you can do the other primitives like, do they fit the time? Is there enough space for questions and discussion and coffee and lunch and everything else?
Yeah. Anyone else? Any other questions? Okay. Well, thank you very much.
Cool. Thank you.